welcome back. I hope y'all had a nice weekend. Just to kind of make sure everybody's on the same page with regards to what's left in the semester, I thought I would just draw us a picture. So we have this week, both Monday and Wednesday. We will wrap up with enolate chemistry today and probably get into carbohydrates. And then on Wednesday, we will hopefully finish up carbohydrates. Then we have the Monday next week, which we will talk about proteins and probably a little bit of organometallic chemistry, just because that's more modern chemistry, and the ACS has begun putting that on their exams. And so I would like to cover at least a little bit of that, so that should you see it on the ACS final, you won't be completely blindsided. So we will do a little bit of that on Monday, and then next Wednesday, that is exam 4, which is enolate chemistry, carbohydrates, proteins, and some organometallic chemistry. Basically everything since the prior exam, right? And then the following Monday, 2 weeks from today, that will be your final, okay? And that's all the time we've got left. So, does anybody have questions on scheduling before we get started?
You can get 2 hours.
Yeah. All right, well, if not, then why don't we go ahead and jump back into it. With a little bit of enolate chemistry to finish up, specifically 3 reactions left. So, let me go ahead and start recording, and we'll get going. Okay, when we last left off, we were talking about the malonic ester synthesis, and I can't remember what number I was on. Number 4. So just to quickly review, malonic ester is going to be very similar to the next reaction we look at. Both of them involve these beta dicarbonyl compounds. So malonic ester, if you recall, looks like this. It's this diester. And because you've got that alpha position that is flanked on both sides by carbonyl groups, it makes those alpha protons much more acidic than normal alpha protons. So we've talked about the alpha position extensively through this chapter, and we know that the alpha position of carbonyl compounds typically has a pKa, depending on the specific type of carbonyl, somewhere between 19 and 20 for aldehydes and ketones. It goes up from there if you're talking about things like esters, pKa 25, and et cetera. These doubly activated alpha positions are much more acidic. So the pKa here is actually approximately 13. And so that means when you treat them with kind of normal type bases, you know, things like alkoxides, you can completely deprotonate them. It is not an equilibrium thing, right? So when you treat this with ethoxide, what you end up making is the anion. And then we can use that as a nucleophile to go and attack generally SN2 type substrates, right? So for instance, we could throw in any number of things. We'll just keep it simple here. It's a good SN2 substrate. the nucleophile attacks to kick out the leaving group. And now that 2-carbon electrophile is now added to the doubly activated alpha position. At this point, you could, if you wanted to, do another addition because you still have another very acidic alpha proton. Or if you want, you can work it up. And when we work these up, this is always done under dilute acidic conditions and heat. That accomplishes two things. As we've seen since the previous unit, if you have an ester under dilute acidic conditions, it easily hydrolyzes to the carboxylic acid. And so initially at least, we would isolate this diacid, but this is a special type of arrangement of your 2 carboxylic acids. You've got the carboxylic acid, and in the beta position you have a carbonyl group. And under these conditions, anytime you have these beta carbonyl acids, usually people refer to them as beta keto acids, but it doesn't necessarily have to be a ketone, it's just some carbonyl beta to a carboxylic acid. These are very labile. They do not tolerate heat. And under the heating conditions of the acidic ester cleavage, what ends up happening is you just lose one of those carboxyl groups as carbon dioxide. And so what you end up isolating here is, well, carbon dioxide comes off, we don't really care about that. What you end up isolating is that substituted acetic acid. And it gets substituted with whatever you added as your alkyl halide. So in this case, we end up with, there's your substituted acetic acid, and then it's substituted with a 2-carbon group because that's what was added in this step. Okay? But the product is always the same. It's going to be some substituted acetic acid derivative. All right? Any questions on this? Okay, then let's go ahead and look at the next one. The next one is going to be very, very similar to the malonic ester. We call this the acetoacetic ester. And this one, in terms of the functional group analysis, is going to start with acetoacetic ester. I'm just going to abbreviate that as AE. And what you're going to isolate in the end is a substituted acetone. Mechanistically and operationally, it is virtually identical to malonic ester. The only difference is we are starting with a slightly different starting material. So what acetoacetic ester looks like is this. So you'll note it's a remarkable similarity to the malonic ester. The only difference is instead of having a diester like we did with malonic, we have a ketone ester. And as a result, it makes those alpha position, those alpha protons, even more acidic than they were with malonic. So here, instead of being pKa 13, here the pKa is around 11. But pretty much other than that, everything's identical. So we're still going to start this by treating it with an ethoxide base. It's going to do the same thing, convert the acetoacetic ester into its anion, which is nucleophilic. And now we throw in whatever we want to substitute. SN2 chemistry. That's what we get initially. And again, like we talked about a minute ago, you still have an acidic alpha position there. So you could do this again. You can do a double substitution if you wanted to. But if you don't, we would just work up under the same conditions. Dilute acid and heat. That's going to accomplish the same two goals, namely hydrolyzing the ester you'll note here, again, you end up making this beta keto ester, which again are very labile and susceptible to heat. And under the conditions of the ester hydrolysis, that is going to decarboxylate, losing carbon dioxide. More importantly, you end up making an acetone with whatever was added as the alkyl halide. Now, these reactions are pretty cool because they not only allow you to make kind of simple substituted acetic acid, substituted acetone derivatives, they also give you the ability to make a rather unique type structures that I'll illustrate right here. So imagine for a minute if we started this reaction. I'm not going to go through the entire mechanism again because we just looked at it. But imagine for a minute we started with our acetoacetic ester. We treat it with a base to deprotonate. And here, instead of using a simple alkyl halide, what if we did something like this? Follow the same mechanism, same steps that we did previously. See where we're going here? We still have an acidic alpha proton. You have a good lead-in group, primary alkyl halide. And so if we treat this with a second equivalent of base, you're going to do an intramolecular SN2, which would give us, in this case, something like this, which we can hydrolyze. Ultimately, that will do the same two things as we've seen multiple times already. It's going to acidically cleave the ester, then it's going to decarboxylate, and then what you're left with in this case is something like that. And you can make some pretty odd ring sizes this way, which is kind of cool.
You can do a 4-membered ring.
Mm-hmm. So it does allow us a good deal of versatility here.
Can you do 300 as well?
Mm-hmm. All right. Any questions on either of these beta dicarbonyl reactions? Okay, then 2 more to go, then we'll be done with enolates. This next one is a pretty important one. We'll spend a bit of time here. This is known as the Michael reaction. Sometimes you'll hear it referred to as a Michael addition, but I'm gonna go ahead and describe the functional group transformation, and then we need to talk a little bit about a unique mode of reactivity that the Michael exhibits. So the Michael reaction from a functional group perspective combines two things. It's gonna use what is called a Michael donor, and it combines that with a Michael acceptor. And what you end up getting from this addition reaction is a 1,5-dicarbonyl compound. So we have a little bit of explaining to do here, but in a very simplified way, what you can think of this terminology, this Michael donor acceptor, you can think of the Michael donor simply as a nucleophile. You can think of the Michael acceptor simply as an electrophile. Okay? Now, I'm going to go ahead and give you kind of some common donor acceptor examples, just so you kind of know what we're working with here. So when I talk about a Michael donor, these are going to be nucleophiles that specifically have a very activated alpha position. So they're going to be kind of like the structures of the malonic ester and acetoacetic ester that we just saw. So things like this. So that would be a Michael donor because you have that highly activated alpha position sandwiched between the two carbonyls. You know, and you can have all sorts of permutations here. Acetoacetic ester would be a Michael donor. Malonic ester would be a Michael donor. Throw in an aldehyde. But it's basically just going to be all these different dicarbonyl compounds. And just for the record, it doesn't specifically have to be a dicarbonyl. It just requires two activating groups. So you could see something like this. Remember, the nitrile group is a strong electron withdrawing group. You can see something like that. The nitro group is also a very strong electron withdrawing group. Okay? So it doesn't have to be a dicarbonyl compound. You just need to have an alpha position sandwiched between two strong electron withdrawing groups. Okay. The Michael acceptors these guys are most commonly going to be alpha beta unsaturated carbonyl compounds. So they are going to look like this usually. And again, I can have all sorts of permutations here. I have an alpha beta unsaturated ketone, but you could have alpha beta unsaturated aldehyde, alpha beta unsaturated esters, alpha beta unsaturated carboxylic acids, all manner of alpha beta unsaturated carbonyl compounds. And like the Michael donors, it doesn't specifically have to be a carbonyl compound. It just needs some activating group next to a double bond. So you could have something like that, something like that. And you can see some even weirder ones, something like this. but just some double bond with a strong electron withdrawing group on it. All right. So, that's kind of an introduction to this Michael reaction. What I'm going to show you now is the unique mode of reactivity that these Michael acceptors undergo. All right, so if I were to give you, let's just work with this one. That would be a good Michael acceptor because it is a alpha beta unsaturated ketone. Now, the unique thing about these Michael reactions, about these alpha beta unsaturated carbonyl compounds in general, is I can draw the normal resonance form for this. All right, when I say the normal resonance form, I'm referring to the one that we've been looking at since we introduced carbonyl chemistry back in aldehydes and ketones. Specifically, that one where we break the pi bond to oxygen and give the electrons to the oxygen. All right, this is the resonance form we've been considering of carbonyls for months now. Right, this is the whole reason why carbonyls are electrophilic and nucleophiles attack them. What's different about this carbonyl than all of the other aldehydes and ketones we've seen so far?
With the conjugation, could the...
Yeah, exactly. I have another pi bond in proximity, meaning there's a third resonance form. What this is showing is that these alpha beta unsaturated carbonyl compounds do not have a single electrophilic site like all the other carbonyls we've seen. They actually have two electrophilic sites. They have the normal carbonyl carbon that is partially positive, but then they also have the beta position that's partially positive. And nucleophiles are attracted to both as a result. Now, the question is, how do you know where a nucleophile is going to attack? If you have two potential electrophilic sites, which one does the nucleophile choose? Well, the answer to that is it really depends on the nucleophile. Okay, as it turns out, some nucleophiles prefer to add to the carbonyl, like we've seen all semester long, but others prefer to add to that other electrophilic site, the beta position of these things. Right? So, and by the way, I'm going to refer to this the way it's usually talked about is let's imagine the two scenarios here. If I had a nucleophile add normally, meaning it's going to attack the carbonyl, and nothing new there, what you end up making from that is that initially anyway, and usually what ends up happening from there is you just end up protonating. Okay. This is, well, the way we typically refer to this is we look at, in a relative sense, where the nucleophile added to where the electrons went. Okay, so in this case, the nucleophile added here, and the electrons of the pi bond went up there. So for that reason, I'm going to refer to this as 1-2 addition.
Where's the numbering? Like what's number one and what's number two?
It's just kind of arbitrary. The 1 is where the nucleophile adds to. So it's not an IEPAC thing or anything like that. It's just you consider the one position where the nucleophile added to.
So the carbonyl carbon is number one?
Yeah. And then the electrons moved right here, which is kind of one away, and so I'm gonna call that the one, that the two. So 1-2 addition. The other way this could add is the nucleophile can add to that electrophilic beta position. So now this one, this is where the nucleophile added to. I would consider that my 1. Then the electrons ended up 1, 2, 3, 4 away. So I'm gonna call this 1,4 addition. By the way this usually resolves itself, I mean, you could imagine, if I just protonate this O- like I did in the previous example, that makes an enol, which we know they don't really exist in large amounts. They always tautomerize. So this is actually going to end up giving you, as the final product, something like that, where the nucleophile is just added to the beta position and you retain the carbonyl group. Now, so that's kind of where we're going with this. What I want to do now is look at what determines whether a nucleophile is going to give you 1,2 addition or whether it gives you 1,4 addition. So, one of these happens faster than the other. Okay, it turns out that 1,2 addition is a lot faster than 1,4 because the carbonyl carbon has a larger delta plus on it than the beta does. Right? You kind of look at it as the carbonyl carbon is a more electrophilic site than the beta position. And as a result, all nucleophiles will attack the carbonyl carbon fastest, or first, however you want to think of it. All right. Do you have a question, Daniel?
Yeah, I'm sorry, I just am having trouble seeing, where did the electrons in the middle pi bond go on the second,
Oh,
on the 1,4 addition?
So there's a couple ways you can think about it. Either you can think of this is just going to go grab a proton in the same way that it did in this example. You're doing this in water or alcohol or something, so it's a protic solvent. There are protons around. So if this grabs a proton, you've got an enol here.
Right.
And enol's tautomerized to give you ketones.
Okay.
Or the other way you can think of it is this is just going to reform the carbonyl and kick out electrons the alpha position to grab a proton.
Okay.
So either way works, but the bottom line is you get the ketone back. So those nucleophiles, all nucleophiles are going to attack the carbonyl first. This happens fastest. The 1,2, as it turns out, is the kinetic product. But the 1,4 is a more stable product. The 1,4 is a more stable product because it retains the carbonyl. Right, the 1,4 addition leads to a product that retains the carbonyl. And remember, the carbonyl is a very strong bond. And so if you can keep it, that's a very good thing enthalpically. It gives you back a lot of energy. So this is the thermodynamic product. So the bottom line is, how do you know what nucleophile is going to do, is going to give you what product? Well, it largely depends on, is this first process reversible? Because as we said, all nucleophiles are going to attack 1,2 fastest. And so if this is not a reversible process, if once the nucleophile attacks and it's stuck and it can't disassociate, then you're going to get 1,2 addition. However, if this process can go back and forth, if the nucleophile can attack and then it can disassociate and it can equilibrate, and over time you give it the option, it will give you the more thermodynamic product preferential. So really the question is, is the 1,2 addition reversible? I guess another way of phrasing that is, can the nucleophile be a leaving group? So let's start looking at some specific examples. If I were to think about attacking my my alpha beta unsaturated carbonyl with a Grignard reagent, remember that what that looks like, what that acts like, is a carbanion. So all nucleophiles are going to attack the carbonyl first. So what we would make initially is that. Is this process reversible? Phrasing it another way, what kind of leaving group is CH3? It's terrible. You're never going to see a carbanion leaving group. And as a result, this process is effectively a one-direction arrow. It goes in this direction and it cannot go back. So, generally speaking, what we're going to see is that very strong nucleophiles favor 1,2 addition. So these are going to be things like, well, your typical strong nucleophiles, Grignards, alkyl lithiums, hydroxide, alkoxide, LAH, all of these types of things. Weaker nucleophiles, or actually probably a better way of phrasing it would be stabilized nucleophiles. Are going to favor 1,4 addition. These are things that once they add in a 1,2 manner, can get kicked back out because they're not terrible leaving groups. Right? And so things that fall into this category are going to be things like a cyanide ion, right? That's stabilized. This anion would be a kind of a resonance stabilized anion. Things like sulfur nucleophiles, Sulfur is a very large atom. It's what we might remember that term. It's highly polarizable. So it's got a lot of electrons and it can kind of spread them out across a large atomic radius. Interestingly, organocuprates are, give you the 1,4 addition products. But the one we're going to care most about are enolates. Enolates are stabilized nucleophiles, and they tend to prefer 1,4 addition over 1,2. So that is the Michael reaction in a nutshell. So let's go ahead and look at a specific example. If I were to take my Michael acceptor that we've been looking at so far. If I were to take and treat this with, say, hydroxide. Hydroxide is going to depronate the Michael donor. Give you that. And then the Michael donor, this is an enolate, and as we just talked about, it's going to prefer to add 1,4. So it's going to attack the beta position. You end up making this. And then again, you can kind of resolve this addition in one of two ways. You could think of just having the O- go grab a proton from water, making the enol, which then tautomerizes, or you can think of doing this, reform the carbonyl, kick the electrons out to go and grab the proton from water. Either way, you end up making something that looks like that. And if you count, here's one carbonyl. That was the carbonyl of the Michael acceptor. 1, 2, 3, 4, 5 carbons away. There's another carbonyl. So we end up making the 1,5 dicarbonyl compound. All right. Uh-huh.
So if it's all enolates, not just the list of, not just the list of Michael donors, then that is gonna apply to all the reactions we've just learned, right? Like we could have something that was a Michael acceptor being added to any of the things we've learned?
Not really, because most of the things that we've looked at have not been alpha beta unsaturated carbonyl compounds. So let me give you a couple of examples of this. What if we wanted to do I think these are probably the hardest ones to see. You know, it's pretty, I think, straightforward to represent, to visualize the alpha beta unsaturated carbonyl of an aldol, or the beta ketoester of a claisen. These are sometimes kind of a little bit more difficult to see in the product. But if we take a look at the thing that we're looking at here, again, count your carbonyls. I see that they're relatively spread apart. If they're 1,5, then that strongly suggests a Michael reaction. There's 1, 2, 3, 4. Then they are. So this would suggest we can get to this place, to this product, using the Michael chemistry. Now, if we're gonna do that, that means we need the two pieces. You need a donor and you need an acceptor. And a lot of times both of them will be fully present in the product. You know, like the example we just looked at. I can look at this and say, okay, number one, yes, I have the 1,5-dicarbonyl compound, so this should be a Michael. Number two, if I'm looking for a Michael donor in this, I'm gonna look for that beta-dicarbonyl system. Well, there it is. So that's easy enough. That has to be my Michael donor, and then the other piece has to be the Michael acceptor. Looking at this one is a little bit more challenging. Because looking at this one, I don't see a 1,3-dicarbonyl in this. I don't see that beta-dicarbonyl that I saw in the previous example. So this is where you have to remember the fact that sometimes you can lose a carbonyl. Sometimes when you have those beta-dicarbonyl compounds, they can decarboxylate. So one way of breaking this up would be like that. So I could make a Michael donor. Something like that. It's a 1,3-dicarbonyl or a beta-dicarbonyl, whatever you want to call it. So that's a viable Michael donor. Because this has that ester group here adjacent to a ketone. If you think about doing this in terms of in the forward sense, you could potentially, in the end, do that acidic ester hydrolysis, converting this to a carboxylic acid, which could then decarboxylate. So this could be the Michael donor that reacted to ultimately give you this type of a compound. We would need to choose the appropriate Michael acceptor. Well, that's just going to be whatever wasn't part of the donor. So basically everything to the right of that pink line that I drew. Would that be a viable Michael acceptor that I've drawn? No.
No,
I'm missing something, right?
it needs a double bond.
There we go. So this would be a viable Michael donor acceptor pair that we could use to get that 1,5-dicarbonyl. By the way, how did I make that 1,5-dicarbonyl? I mean the Michael donor here. We looked at a reaction that would do that. Look at it in terms of functional group. This is a beta keto ester. What reaction gives beta keto esters? Yeah, exactly. This we could make through Tiedemann cyclization. So all of these reactions kind of build on each other. All right, let's look at another one. if we were faced with this one, what we would want to do first is kind of go through our Rolodex of reactions. Is it an alpha beta unsaturated carbonyl? That would suggest an aldol. No. Is it a beta keto ester? Would suggest a claisen? No. Is it a substituted acetone? That would suggest acetoacetic ester? No. Is it a 1,5-dicarbonyl? Oh, why yes it is. So, that would suggest a Michael reaction. Now, like we did with the last one, in this specific product that we're trying to make, do you see, obviously if we're going to try to do a Michael, then we need a donor and an acceptor. The donor being one of those compounds that has a 1,3-dicarbonyl. Do you see the 1,3-dicarbonyl in this? No, we don't. So that is going to suggest we probably started with a Michael donor and ended up having to decarboxylate it at some point. There's another clue in this target. What's the other clue here? Go through that Rolodex of reactions. We went through most of them. So we talked about that it's not an aldol, it's not a claisen, it's not acetoacetic ester. Which one have we not thought about? The malonic ester. And what does a malonic ester give you? A substituted acetic acid. Do you see that in this? Yeah, I actually see two of them. That's a substituted acetic acid. That's a substituted acetic acid. So, a malonic ester is technically a Michael donor. So we could potentially use that as a Michael donor. If we did that, that would probably be, I don't know, there's a couple of ways you could think of doing this, but we cleave the top part of it. That could be the Michael donor, which means everything below the pink line would have to be the Michael acceptor. Is that a viable Michael acceptor that I'm drawing? No, because I don't have my double bond there. Now it is. All right. Any questions on the Michael reaction? All right, then the final reaction of the chapter. I saved the best for last. This is really the pinnacle of enolate chemistry. It's a tandem reaction, so it's kind of a 2-in-1, and it is known as the Robinson annulation. So this, when you see the term annulation, that just means a ring-forming reaction. So we're going to be making rings. This reaction was very, very important, both from a synthetic and a historical sense. In fact, Sir Robinson was given the Nobel Prize for this chemistry. It was really used quite a bit between the 1940s and 60s, specifically in the synthesis of the steroid hormones. People back in that time were very, very interested in studying the physiology of steroid hormones for a bunch of different reasons, right? Reproductive health, metabolic health, all sorts of things that the steroid hormones govern. But the problem with trying to study them in a physiological sense is you had to have them to study. And animals just don't make a whole lot of this stuff, right? And so if you wanted enough quantity to do all of these biological studies on the steroid hormones, you really had to synthesize them in the lab. And that is where the Robinson annulation found a lot of use in that time frame, was in the total synthesis of these steroid hormones. So, but the annulation really, like I said a minute ago, is a two-reaction process all rolled into one. It is going to combine a step one, which is a Michael reaction, followed by an intramolecular aldol. And what you end up making at the end is a ring with an alpha beta unsaturated carbonyl. All right. So the best way, I think, of seeing this is just looking at one example. So let's go ahead. We'll start with as simple of an example as we can, and that will involve, since we're going to, step one of this is a Michael reaction. That means in order to begin this annulation process, we need a donor-acceptor pair. So let's just do which one's the donor and which one's the acceptor on this? The which one?
The left one.
Yep, the left one's the donor, right? Because that's the dicarbonyl compound. The right one, that's my acceptor, because it's an alpha beta unsaturated carbonyl compound. So on the basis of that, I know how this reaction starts. I'm going to take these two, mix them together in the presence of some base. I need the base because that's going to deprotonate the doubly activated alpha position of the donor. And once you deprotonate and make the anion, it's going to attack the Michael acceptor at its beta position. So we would get that initially. And then the way this guy resolves itself is, again, you can do it in a couple of different ways. Have the carbonyl reform and then grab a proton from water, which is going to give you the product of the Michael reaction. Which looks like that. We can verify that this is a true Michael product. Here's the carbonyl of the donor. 1, 2, 3, 4, 5 carbons away. There's another carbonyl, so it is a 1,5 dicarbonyl. under the conditions of the annulation, which is a lot of base and a lot of heat, you cannot isolate this. Because what happens is we've got a bunch of alpha positions. I mean, if you think about it, you've got an alpha position there, 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 there. So all of those are going to enolize under the conditions of the reaction. But only one is going to give us a viable product. All right, when we talk about these annulations, the Robinson annulation, you're only going to get fused ring systems. So no, what I mean by that is you cannot get bridged bicyclics. And the other limitation is only 5 and 6 membered rings. So, if I were to enolize at that position, right here, oh yeah, right there, it would try to wrap around and attack the other carbonyl. 1, 2, 3, 4, 5. Well, that's a 6-membered ring. That's good. The problem is that would lead to a bridged bicyclic system. Right? I would make that ring, but then this carbonyl group would kind of be puckered up out of the plane. It would be a bridged bicyclic. The same thing is true here. If I were to enolize there and try to attack the carbonyl 1, 2, 3, 4, 5, 6, that would give you a good ring size, but now that carbonyl would be puckered up out of the plane. Both of those would lead to bridged bicyclic systems, which we cannot have. If I were to enolize here, it would wrap around and attack the other carbonyl. 1, 2, well, that would lead to a 4-membered ring. Not gonna work. If I were to enolize here, that would wrap around and attack the other carbonyl. 1, 2, 3, another 4-membered ring. So it looks like I'm striking out left and right here. We've only got one option left, and that is enolizing here at the end. 1, 2, 3, 4, 5, 6. Well, that leads to a good ring size, and it leads to a fused rather than a bicyclic ring system, or bridged bicyclic system. So that's what's going to happen. Enolize here, and that's going to wrap around and attack. And like before, I've mentioned this before a couple of times, anytime I'm making rings or breaking rings, I always number my carbons, just because it helps me to not make mistakes. Numbering this one the same way that you did previously. 1, 2, 5, 6. Now fill in what's on the ring. On carbon 2 is the carbonyl. Carbon 6 is the tetrahedral intermediate. That's going to grab a proton from water. Look what we have now. That would be an alpha position, that would be a beta position. What we have formed at this point is a beta hydroxycarbonyl compound. which is one of the products of an aldol. However, like we've talked about extensively, these are almost impossible to isolate because you still have those acidic alpha positions. You're still in a lot of base. And so hydroxide comes in, grabs that proton, forces the electrons there to kick out the hydroxide. And what you're left with is number one, a new ring, and number two, an alpha beta unsaturated carbonyl.
Would the hydroxy grab the proton from the other side, where it's right next to the carbon?
You mean like from one of these guys?
Yeah, right there.
Right here? You know, it could. I mean, it could enolize for sure because that's an acidic position, but it's just not really gonna be able to do anything once it does.
It would form that double bond.
No, not. Oh, I see what you're saying. So instead of grabbing this proton and forming a double bond between there?
Yeah.
No. Having a double bond within a fused, like on the carbons of a fused system is really unstable. Yeah. It's just, it does weird things to the ring flexibility and stability. Okay, any questions on how we did the annulation here? This is getting fun. Let me give you another one. See what you can do with this. look at this one. First off, do you recognize that as a donor-acceptor pair? Does that make sense? We have the beta dicarbonyl compound here, making it a Michael donor, and you have the alpha beta unsaturated compound here, making it a Michael acceptor. So under the reaction conditions, the base is going to grab the most acidic proton, which is the one sandwiched between the two carbonyls at the donor, giving you a nucleophile that looks like that, which is going to attack the acceptor. And you should get something that looks like this. And then that's going to protonate from the solvent. And that should give us the Michael product. Yeah, something like that. Now we can verify this. Here's the carbonyl of the donor, 1, 2, 3, 4. It is a 1,5-dicarbonyl, so that is a good Michael product. Now in the next part, what we're going to do is we are going to deprotonate one of the alpha positions, and that is going to wrap around and attack the carbonyl on the ring. And I might just go ahead and number these. So off of carbon 5, we have that ester that's just hanging out. Carbon 2 is the carbonyl. Carbon 1 is a methyl group sticking off. And then carbon 6 is my tetrahedral intermediate, which is going to go and protonate. So we get something like that.
Remember your methyl.
Oh, methyl group, there we go. And again, here we are, we're at that position where we have a beta hydroxycarbonyl compound, which we know usually are not, can't isolate them. But we do have an acidic proton still. So hydroxide, or F oxide in this case. It's going to come in, grab that proton, and kick out hydroxide. Giving us that. Any questions on how we did this?
Other than the initial base, are we adding any extra heat or anything along the way? Or,
Oh yeah, these are done reflux, generally speaking.
but we're not like adding any other reactants or anything?
No. No, you just mix the donor and acceptor together at the beginning, add the base, and then heat it up.
Okay.
All right, well, I think we have time for one more. You should be able to predict the products in the forward direction like we've done in the previous two, but you should also be able to predict in the reverse. If I gave you an Robinson annulation product, you should be able to tell me where it came from. So that's what I want to look at with you now. It's really not that bad, as long as you go in the perfectly stepwise direction, okay? It's probably going to be very, very difficult for you just to look at an annulation product and say, oh, well, naturally it came from these two. What I would strongly recommend you do is just take it and work it exactly like we did these past two examples, just do it in the opposite direction, right? So let me go ahead and give you an annulation product. So let's see if we can figure out where this thing came from. Now, the first thing that we're going to do is remember the way we got this alpha beta unsaturated carbonyl system is through the elimination of a beta hydroxycarbonyl. So I'm just going to take this and redraw it exactly without the double bond. So that would be it. Now the question is, how did we get to the beta hydroxy? Well, you get the beta hydroxy by having the enolate attack a carbonyl. So the bond we really need to think about breaking is that. Carbonyl there. This is a carbonyl. There's the methyl group, and then attached to the methyl, I have this 1, 2, 3, 4, 5, 6 ring. So if you want, you can number these. Sometimes it's helpful. So carbon 3 is the one that had the carbonyl. Do you see a Michael donor in this? Somewhere in here? Mm-hmm. Yeah, exactly. We're looking for that 1,3 dicarbonyl system. So right here, that's looking like it could be a reasonable Michael donor. So then the disconnection that we're going to make is there. So the Michael donor could be that. And then whatever's left Must be the Michael acceptor. Now, obviously, that's not a viable Michael acceptor the way I've drawn it, because a Michael acceptor has to have the alpha beta unsaturated carbonyl, but that's easily fixed like that. All right. Any questions on this, working this one backwards?
If we're doing a synthesis problem, how would we make the donor synthesis problem?
I probably wouldn't have you make the donor.
Okay.
Yeah, it would probably be, these kind of questions would probably lend themselves more to kind of what we were just looking at, like, I'll give you a annulation product and say, what were the two reactants that formed this? Or I'll give you reactants and say, what is the annulation product that would be made from this, or something like that. All right, I'm gonna give you one to work on your own, and then we will come back on Wednesday, look at it together, and then move into carbohydrates. All right, which reminds me, if you like to have the PowerPoint slides handy, you might want to download them for Wednesday, because I'll be lecturing primarily off of the PowerPoint slides for carbohydrates. Okay. All right, so the one I'm going to have you work on your own is this. This is going to be a little bit different because there's only one ring. So sometime whenever you have a minute, think about what donor acceptor pair formed this annulation product. All right? And I think that's probably a good place to stop, so I will see y'all in about 10 minutes.